Welcome back. Today we're going to solve two problems related to ideal transformers or ideally coupled inductors. In this case, problem 41 states calculate the average power. So when we talk about average power, actually we're referring to P in the sense of phasors. So the active power when we calculate power using phasor representation, delivered to the two resistors on the secondary side. So this one and this one. So very simple circuit. And the idea here is to use the referring, I wouldn't call it technique, but we need to refer the elements from the primary to the secondary. So meaning we take this 2 and move it to the secondary using the turns ratio, or we take those two elements and move it to the primary and calculate the turns rate using the turns ratio. Any of those would work. In this case, it's easier since we want to calculate stuff related to the secondary element. We're going to move the source and the impedance on the primary to the secondary side. So let's state the phasor representation. And let's be let's be specific here, RMS values on the of the circuit referred to the secondary side is, what is it? It's basically this system. So we know that we're not touching anything on the secondary, so the impedances are the same, 21 ohms and 400 milli or 0.4 ohms. But we need to adjust the impedance and the source of the primary side. So first of all, let's transform this into RMS value. So divided by the square root of 2 and times A. Why times A? Because we're moving this source from the primary side to the secondary side. How do we do that? We multiply by A. What happened with the resistor? 3 times A squared. So what is A in this case? It's by using the definition, right? 1 to A equals in this case to 1 to 100. So 1 to 100, that means that A, it's 100. Okay, you can always use this relationship to figure out. Sometimes it's 5 to 500, so A is going to be still going to be 100, but the ratio is going to be different, right? Or it can be 300 to 10, for example. So A in this case would be 10 divided by 300, so on. So we have everything in the circuit. I2, we haven't touched I2, so we do have I2 here. And we can use this circuit now to calculate the current. So current in this case would be I2 simply would be the voltage at the source, 2 over the square root of 2 angle 0 times A, which is 100, 0 degrees, divided by the sum of all impedances. So 3 times A squared, so A is 100 plus 0.4 plus 21. And what do we get from this? Based on my results, should be 4.71 times 10 to the minus 3 angle 0. It's a resistive circuit, so we don't have any angular displacement here, amps. Great. Once we have the current, then calculating power, it's extremely easy. We have only resistors, so the impedances only have real part. Easy enough. So we can go ahead and calculate power. So then we can say P at the 4.4 ohms, it's going to be simply 0.4 ohms multiplied by I2, the module square, right? So based on my calculations, this should be 8.873 times 10 to the minus 6 watts, or equivalently 8.873 microwatts. And then P at the 21 ohm is going to be R, so that's 21 times I2 square. Based on my results, this is 4.658 times 10 to the minus 4, which equivalently should be 465.8 microwatts. So that's a clear example on how you would use the turns ratio between primary and secondary to move elements from one side to the circuit to the other. Of course, if you would have to move this one to the primary, we would have to divide by A squared in this case. So it's going to be specific for moving from the primary to the secondary, or from the secondary to the primary. Let's apply that to another problem. So I have prepared problem 48. In this case is calculate Bx. So we have two transformers, or two coupled inductors here. And we have all the values that we need, essentially. So we need to calculate Vx. We have A and B. We have this ratio here. We have R1, we have R2, and we have the load. Perfect. We have all the values on this circuit. What do we do? Solution. So in this case, we're calculating voltages. So I know that in general, when we move into phasor domain, we use RMS values. That's the standard thing to do. There's nothing wrong to use maximum values, which is what we're going to use now. So we need to be consistent. A major thing using RMS values is when you calculate power, then it's only V times I squared. Sorry, V times I conjugate. So that's just a major thing. You don't have to care of the 1/2 to change or to adjust the calculations of power. So in this case, let's be specific. So let's use this same phrase here. So the phasor representation using, I'm going to be here, max values. And again, we can do that definitely. So we don't have to transform everything to RMS value. Since we're calculating voltages, we know that everything is max values. That's it. That's the only consideration. It's not that it's wrong or good using RMS values. It's just that it's a way to solve the problem. Of course, in real applications, especially in power, RMS is the standard. Everyone uses RMS values. It's kind of the expected thing. Every time that you look at the voltage or a current, you're going to be talking of RMS values. Referred to the, let's say, intermediate circuit. Portion of the circuit. Yes. So that means we're going to move these two elements to the intermediate part using this relationship. Of course, in this case, A is 1, so the transformation is not going to do anything. However, when we want to move this to the other side, then of course we need to consider this ratio here. So we're gonna have, let's put it this way. That's that. Then we have another resistor, we have V, and then we have the load. So this is going to be 2 angle 0. Again, I'm not dividing by the square root of 2. That's okay. You have to be just consistent. Times 1 in this case. A is 1, right? So R1 times 1. Here's R2. We're not touching the intermediate portion, so we still have 1.85 ohms. And we still have our Vx here. And finally, the RL, we need to divide by A squared. So what is A squared in this case? So 1 over A, in this case, is going to be A to B. The values, right? Let's call this A the transformation ratio. So that means that 1 over A equals A over B. So A, the transformation ratio, is going to be B over A, right? B over A. So we need to divide by A squared. That means that RL is going to be divided by B over A squared, which is equivalent to RL times A over B squared. Okay? So since we're moving from the secondary side to the primary of this transformer, then we're dividing by A squared. A in this case is B over A. Because of the algebra here, then we get this. Multiply by A over B. I encourage you to always do this analysis so you don't mess up with the transformation ratio. So we do have this. We have this voltage. So when we analyze this circuit, essentially, if we combine these two in parallel, right, then we're going to have a series circuit, an equivalent here, an equivalent impedance, and we're going to have stuff in series. So 3 impedances in series. So we can use, essentially, we can use voltage divider to get this voltage, right? So then using voltage divider, we have Bx, it's going to be the source, 2 angle 0, times the voltage at this impedance divided by the sum of all the impedances, right? So on the numerator, we're going to have 1.85 in parallel with RL times A over B squared divided by the sum. So R1 plus R2 plus the parallel. So that means, let's use this, 1.85 in parallel with RL times A over B squared. That's simply the solution. We write down the equation. Now we calculate very carefully on your calculator. So plugging in the values, we get, what do we get? Vx equals, you should get 604 angle 0 microvolts, or 604 times 10 to the minus 6. Actually, let's fix the notation here. We're using phasors, So that's the notation, the proper notation, which in the time domain would be Vx of t, which in this case is 604 cosine of the source. The source frequency is 10, so 10t plus 0 degrees, right, microvolts. So that would be the solution in this case. It makes sense to be such a small voltage because we have 1k here times a over b squared. A over b is 0.01 divided by 1 square. So you're going to have a very small value here. R1 and R2 are quite big. So 314. And here we only have 1.85. Here we're going to have 1k multiplied by 0.01 squared. So a very small resistance. The parallel is going to be even smaller. So basically no voltage it's reaching this part. All the voltage it's being essentially distributed to R1 in this case. So we have a huge resistor, 300. We have a smaller one, which is 14. And then we have the parallel, which is going to be smaller than 1.05. So 314, let's say around 1. Basically all the voltage is going to be on this resistor. That's why we get such a small value for Vx. So that's this problem. I hope it helps for the homework. That's the way to go. Thank you.